Should I start? Okay. So today I'm going to prove something. So let me just recall where we were last time. So I have a Euclidean triangle of three sides, L1, L2, L3. And the opposite angles are theta 1, theta 2, theta 3. We are in the circle packing setting. And so I'm going to abbreviate as a CP. We're going to use that a lot today. So in the circle packing setting, we really, you can think of this as you take this triangle and you look at the inscribed circle, so that, and this inscribed circle is going to cut the three lengths into three different. So this is the vertex 1, 2, 3. You have three tangent points, and these are the three locations of the circle centered as the vertices. Okay, so I'm going to call these the radius 1, this is radius 2, and radius 3. And so we think of the angle, which is, as we know, is a curvature as a function of the radii. So the radii are the metric and the curvature. And we proved last time this theorem. I think this is really a remarkable theorem. It's a colon Duvalier. That in this setting, we need to make a change of variable. If you look at Thurston's notes, he already did the calculation. This is, in fact, I checked last night. It's in chapter. By the way, it's definitely worth taking reading Thurston's notes, page 342. He did the calculation that of partial theta I, the angle with respect to the radius derivative, and he noticed that this is going to be less than 0, as we saw last time. This is really geometrical. You fix these two radii and increase this radii a little bit, and then the triangle is going to be making this change roughly. So this vertex angle is going to be decreasing, which is coded by that, and the other two is increasing. It's amazing that we can control. And so Thurston also did this calculation that J is positive for I is not equal to J. But he noticed that if you just take this naive change of naive radii, the partial derivative is not symmetric. And so if you switch I and J, it's not. And so what Colin Duvalier did was this symmetry, which produced a variational principle. So let's let Ri to be e to the ui. In other words, you make a change of variable, which you, I guess at the moment you think it's really simple, sort of a natural choices, but I will convince you that it's not in a minute. So what he did was, it's the same thing, partial theta I, partial ui is going to be negative. That basically follows from Thurston by change of variable. And the amazing part is this, partial theta I, partial uj is partial theta j, partial ui is going to be positive. Okay, so you may think, well, this is sort of a natural now. You can do that, but he also did the same thing for hyperbolic triangles. And if you try so this is also true. The statement is true for hyperbolic triangles. And in that case, it's not the log of the radius. Okay, it's some very interesting function. And it's not easy to come up with. So if you really want to know the answer, ui is equal to log hyperbolic tangent radius over 2. It's highly non-trivial. And if you think about it, how can he come up with this? There's so many functions you need to keep trying, and there's only one choice, which will make this symmetric. So I was very puzzled by how he came up with this amazing formula. So as a conclusion, by the way, these two, he concludes that this matrix partial theta r partial us, this is 3 by 3 matrix. This is a symmetric matrix, and it's a negative semi-definite. With null space, you can with null space, it's basically 1, 1, 1. Okay. Sorry. So the null space being 1, 1, 1 is obvious. The null space contains its vector is obvious because we have the sum of the 3 angles is always a constant. And now you take partial derivative with respect to any r, and that will make it equal to 0. So, so if you look at this matrix and you look at the sum of the entries in one column, it's always equal to 0, and that gives you this null space. And it's easy to see from these two conditions that the rank of this matrix is 2, right? So what does this tell you? It tells you that the matrix is of this form A, B, C, and A, B, C, and then minus A, minus B, minus C, minus A, and minus B, minus C. So this is the 3 by 3 matrix where ABC is positive. And this is, if you put a negative sign to that, this is a diagonally dominated matrix, right? So the diagonal here is the largest one, is larger. The absolute value of the diagonal is bigger than the sum of the rest of it. And so it's a positive or negative semi-definite. And because of this sign, you see the rank is 2, and that gives you this amazing result. So you can also think, this is also true for spherical is true, and in that case, you change that to tangent. So I met him a couple of years ago, and I asked him, how did you come up with this formula? This is non-trivial, highly non-trivial. And he told me that it's coming from the Schlafly formula. So this is really a 2-dimensional Schlafly formula, but he guessed it from 3-dimensional Schlafly formula. And so let me just quickly recall this Schlafly formula here. It really is underlying sort of basic identity which somehow underlie all of these 2-dimensional phenomena. So the Schlafly in the simplest setting is you take a tetrahedra. It could be in Euclidean space or the sphere or hyperbolic space, and you can measure its length. So let's measure the length of the ice edge to be Li, and it has a dihedral angle theta I. And we know in this case the dihedral angle is determined by the length. So the Schlafly formula in the simplest setting says that partial theta I partial Lj is partial theta j partial Li. Okay, and it's really in the natural length. There's no change of variable. This is it. And if you look at that formula and this, there is really a very close similarity between the two. And you can now do the integrations of this. So the standard procedure, because of this, it tells you that the differential one form dLi is a closed one form, and you can integrate it. And from that, you get a function of the length. So there is this magic function of the length tetrahedra whose partial derivative is equal to the dihedral angle. Okay, so this function is basically the Legendre transform of the volume. Okay, and for those who are familiar with the Reggie calculus, that's the discrete general relativity that Reggie proposed to approach it. So this what I'm saying that this is a remarkable theorem, has lots of connections, and we will see some applications of it today, including the proof of the Andreev-Thurston's Koebe-Thurston theorem. Okay, so before I go to the next, let me just mention what Thurston did. So he just observed this just by looking at the pictures and calculated, and from that he obtained a maximum principle, which is very useful, and I'm going to use that maybe on tomorrow to prove the convergence. So this is a corollary. This is a maximum principle of Thurston for circle packing. So let me just draw the picture. It's really very simple and straightforward. So before I state it, let me show you the picture. Okay. So suppose you have a circle. You have a circle in a plane, and a collection of circles tangent to it. This is sometimes called a flower. So you have a center circle and a circle around it, and the nerve, the combinatorics, is just a star of a vertex. Now, the maximum principle for, say, a harmonic function will say if you have a harmonic function which achieves a maximum point in the interior, then the function is a constant, and that's what's occurred here. And so this is sort of a discrete harmonic function. So you have a function defined on the vertices of the graph, which is harmonic, meaning the value at vertex, interior vertex is the average of the value around it, and then if it achieves a maximum point in one vertex at the interior, then the function has to be constant. So suppose we have this circle packing in a plane whose curvature is 0 at the center vertex. And so suppose this is a CP metric whose curvature as the center is flat, is 0. Okay, now we are changing these radii. So suppose I'm going to increase the radius. So Ri is going to be the radius at Vi. So these are the vertices, and we have this flat picture. If we increase the radius in the center and decrease the radii other than the center. And so this is now, I'm trying to make this sort of a maximum. So suppose we have sort of stationary faces at the curvature equal to 0, and I increase the curvature, the radius in the center, and decrease the radii outside of it, and then this is going to destroy the flatness. And so this will, then the curvature is going to be, in fact, so let's just look at this picture. So if I do that, what you will see, these angles is going to be decreasing, because I increase this radius, and I decrease this radius, and so this is going to increase that as well. And so the whole curvature at the center is going to be decreasing, because the angle is going to be negative. So in other words, if you make this curvature to be flat all the time, there's no way you can achieve a maximum point at this point. Okay, so maybe let me write it more carefully. So this is a proof. That's what Thurston observed. It's really useful, as you will see tomorrow. So here is his statement. So the maximum principle says that, let me call this triangulation P of T. So P is this disk, and T is this triangulation. It's just it's a star, okay? A star of a vertex, the simplest vertex. And suppose I have two circle packing metric on this triangulation, on this very simple triangulation, such that their curvature are the same. They have the same curvature as 0. And now if we have a maximum value at the center, and so this is the maximum value should be written like this. Is equal to the maximum value of RVI. So that characterizes what I'm saying. So you really try to compare the two. Then the conclusion is that these two circle packing metric are the same. So for some scalar. Okay, so this is just take the whole picture, multiply by 3, and that's these two metrics are the same. So that's a maximum principle, which is a direct consequence of the of this monotonicity phenomenon. So now let me just make one more. Let's consider one more consequence of this, which is I'm going to use to prove the Andreev theorem. It's the following. So this is a corollary of Coulomb-Duvalier. So it says that, so this is the corollary. So there exists a concave function. I'm going to call W circle packing of U1, U2, U3. Which is the integrate from 0 to u of theta I dui. Well, we know this form is closed, right, because of this symmetry. And this now is defined on the whole three-dimensional space, because there are no constraints on the radii. We can choose any u's, and that will produce a radii, and that's a triangle that will produce a triangle such that partial W circle packing Ui is equal to theta I. Okay, so this again, this is follows from the definition, and furthermore, because we know the null space, this the Hessian of this function is equal to this Jacobian matrix. And we know the null space, and so we can tell when this function is strictly concave. So such that, and if you look at this function, so WCP is strictly concave on each line like this. So TU plus 1 minus T U hat. Where I give you u and u hat. I give you two vectors in three-dimensional space, so that the difference is not in the null space, and so it's not equal to CCC. Okay, so as long as it's not in this parallel, u minus u hat is not parallel to the null space, and then the function is going to be strictly concave. Okay, so this follows from that. And we're going to use this to prove the rigidity. And second, so this is the first. And the second part is let's take 3 positive numbers so that the sum equals pi. And so I can find a Euclidean triangle whose angles are A1, A2, A3. And you normalize a little bit. So I'm going to normalize this a little bit. And let's define G of U to be W circle packing U minus summation AI UI. So I just take a concave function, add a linear function. This is still concave. But with this normalization, it satisfies the following. So define this. Then we have this property. I'm not going to prove it. This is straightforward. So if you add a diagonal vector, this function is going to be homogeneous. This is straightforward because if you add a diagonal to, this is just the scaling change. Okay, I will just leave it. And most importantly is that then this and G and this function satisfies the property that G is a proper function on the plane P. So if you look, so this function now is basically defined in a 2-dimensional plane. Okay? You add a diagonal vector, it's not gonna be changing. So let's just focus on the plane where on the plane orthogonal to the null vector, this function is going to be proper. Namely, if you look at x in P and x goes to infinity, then g of x is going to be equal to minus infinity. And the proof is, so this is straightforward. This is also straightforward because what you have is that this function g is, first of all, strictly concave. On P. This is because every point here is really orthogonal to the null space. And furthermore, this function has a critical point. And G has a critical point. So at U1, U2, U3, at some point where, so you take those radii in this plane whose corresponding triangle has inner angle A1, A2, A3. And then that point is going to be the critical point because of the, I'm going to call this Schlafly, because of this Schlafly type, right? Because what is partial G, partial, say, xi is going to be equal to the theta I angle minus AI. AI is fixed. This is the angle. And at this point, this angle is AI, and so it's a critical point. So what you have is we have a function, a strictly concave function, which in a plane which achieves one critical point, and that has to be the maximum point. And because this function is strictly concave, it's going to be below the cone. Okay, so this is a strictly maximum point, and so you draw a circle around this point and look at the cone over it. And so the graph of the function is going to be, because of concave, is going to be below the cone, and therefore it's going to go to minus infinity. So that's that. And now let's prove the first theorem. This theorem has many applications. Okay, so let me prove Thurston's theorem first. Thurston give a different proof, but I think this, so the next proof here by Coulomb-de-Verdier is really a simpler proof. So this is a Thurston. it says the following. So suppose I have a compact connected triangulated surface with a triangulation T. Okay, so this T is a triangulation, and S is a compact connected surface, and I have two circle packing metrics, and R and R hat are any two functions. So these are two circle packing metrics. But by the way, let me just pause here and make one remark, because the title of my talk is discrete conformal geometry. So you may think, how is this related to discrete conformal? From Thurston's point of view, any two circle packing metrics are discrete conformal. So this is Thurston's point of view. In some senses, it makes sense because if you change the different radii, it's sort of a sort of a scaling change in the tangent space, and so the circles remains the same, and that's the meaning of discrete conformality. Okay, so different choice of radii. If you compare the geometry, the polyhedral geometries of that, and look at the tangent sort of tangent space as the vertices, it gives you the same sort of notion of circles, and that's a discrete conformal. Okay, so suppose I give you two circle packing metrics on this surface, and then the statement is quite remarkable. Then their curvature. So I'm going to call it KR and KR hat are the same. So you ask, when are the curvatures are the same? And the answer is if and only if they differ by a scaling. And of course, if you have two radii assignment and they differ by a scaling, this is obvious, right? So this is trivial because I just take a polyhedral metric and multiply every length by 5. There's no change on angles, and this side is remarkable. Namely, the curvature. Just look at the sum of the angle at the vertices determines the radii up to scaling. Okay, so let me before I prove it, let me just make a couple remarks here. The first remark is it's false for S non-compact. And that's the example I give you in Doyle's case. So this is the Doyle's spiral circle packing. In that case, we take the complex plane, take the standard hexagonal triangulation, and Doyle produces this linear, log linear radius assignment. And the curvature is always 0, but it's not the standard one. Okay, so but there is so the problem here is, of course, if you have a non-constant log linear function, as we saw last time, the radii now you look at the radius function defined on these hexagonal lattices. Because of this log linear phenomenon, you can produce a sequence of vertices goes to infinity, and the radii is exponentially decay. So what really happens here is that if you have a non-constant log linear radius assignment, the metric is not complete. And see our metric. So you can find a Cauchy sequence, so it does not converge. And so there is some completeness involved for non-compact surfaces. And so what Rodin and Sullivan proved, which I'm going to prove tomorrow as a part of the solution of Thurston's convergence conjecture, is that for this case, if you add a completeness, then it's true. And so if you take the complex plane, the standard hexagonal circle packing, and any circle packing metric which is complete is a complete flat metric, and then R has to be a constant. So what I'm saying that for non-compact circle packing metric, you need to add some geometry to it. For instance, the completeness, and for that one can prove the rigidity. And the proof of this is going to use the maximum principle, and that's why I mentioned it. Okay, so let's now prove it. Okay, let's see what he said. Well, let me change it. Well, I think I'm gonna. Let me just see what it said. The proof is quite straightforward, using this corollary, which I'm erasing. Okay, so let's prove by contradiction. Okay, so the proof. So suppose not. And now I have a radius. I have two circle packing metric which are not proportional, but their curvature are the same. Okay, so I will derive a contradiction using this variational principle. So what let's take a vector u and u hat. So I'm going to change your variable, change you sort of the scalings here. These are the radii, and take two u's, and such that that r at v is equal to e to the u of v. So u at v is a log of r of v. Okay, so that we will be in the parameter setting of the previous Coulomb-Dividier theorem. Okay, so what do I have then is that, and the same for that. So what I have then is u minus u hat is not going to be equal to a constant scaling of the vector 1, 1, 1. Okay, so these are the same thing. Now let's do the following. So let's define the function W. So this is the variational framework. This framework, I'm going to use that again. So you define some energy associated to every circle packing metric in U parameter, a function. And the function is just this Coulomb-Dividier function. So such that W at the point X is equal to, you look at the sum, whenever we see a triangle VI, VJ, VK, in your triangulation, I will produce this action functional, the circle packing functional associated to this triangle. So this triangle has vertices VI, VJ, VK, and now I have the xi variables associated to the VI. So I take xi, xj, xk. So this function is a sum of concave functions, and so this is concave. It's a sum of concave functions is concave. And what is its main property? So here, let me recall that this function is a Schläfli type function. So if we let aijk be the angle at the vertex vi in the triangle vi, vj, vk. So suppose this is the angle ijk. What we have is this, right? So we know the partial derivative of the functional at xi in this setting is equal to aijk. So in Thurston's picture, it's something like this is my vi vertex, and if I'm now changing the radii at this vertex vi, and the rest of it is not changing, the rate of change are these angles. So if we take the partial derivative with respect to xi of this w, then we get partial w partial xi is equal to the sum over all j and k aik. Okay, so over all possible angles centered at the vi's vertex, and that's a curvature. So this is by definition equal to 2 pi minus the curvature at this point. I'm going to call e to the x. Okay, so e to the x is a radius assignment at the vi. So this is a really remarkable identity. It gives you almost everything we want to know. So the critical point is exactly equal to those. Well, the critical point at this moment is not right, but so the conclusion is that the gradient of this function is equal to 2 pi of the vector 1, 1, 1 minus the curvature. Okay. And now we are done, because just to think about it, what do we have? We have a concave function whose gradient is essentially the curvature. And if we have a concave function, the gradient is basically 1 to 1. And that gives you this fact. And so let me finish this by saying more carefully how the proof goes. So now let's consider this. So let me just make this a little bit more precise. So let's consider this function, f of t to be w, this concave function restricted on a line. And this is going to be a sum of all triangles of w circle packing of t ui, uj, uk plus 1 minus t ui hat, uj hat, uk hat. Okay, so here vi, vj, uk. It's the same. This is concave in T. And now I'm going to use this condition that these two vectors, the difference of the two vectors is not parallel to the diagonal. And the fact that the surface is connected. So u minus u hat is not equal to 1, 1, 1. And S connected tells me that I can find a triangle VK so that when I restrict it to the triangle, these two, so UI, UJ, UK minus UI hat, UJ hat, UK hat is not parallel to the diagonal. Okay, this is the connectivity in follows that. And so what does this tell you? This tells you, as the corollary tells you that this function, for this very special triangle ijk, this function is strictly concave. So this tells you one of the cylinder is strictly concave. So the conclusion is that, so this function f is a concave function, but one of the is a sum of concave function. One of them is strictly concave, and so it's strictly concave. So f is concave, and as a consequence, we know the derivative is not equal to the same. It's a strictly concave function since the derivative at the endpoints are not the same. Now, what's the derivative? The derivative of that is the gradient of w at u hat and u minus u hat by the chain rule, right? And f prime is the gradient of w at u minus u hat. So, so the two gradient dot with the same vector is going to be different, and so we have the gradient of wu is not the same as the gradient of wu hat, and therefore, by this basic formula, it tells us the curvature are not the same. So that's a contradiction. So this is the quite a standard method in finite, so polyhedral geometry. So you develop a very nice variational principle like this, and you have some convexities, and you can make lots of conclusions like these rigidity phenomena. Okay. So so I will tell you a little bit more later of this type. Right. Okay. So now let me prove. Okay. So let me pause a little bit because there's still a lot of interesting questions here. So the first question is, what is this function? Before I go to the next, so the first question is this: what is this Coulomb-Dirichlet's functional? So can we? So question: what is this WCP? DUI. So can you find the explicit formula for it? The answer is yes. So this paper of Coulomb-Dirichlet was in 1991, and it was found by Breger in his 95 PhD thesis. So it's again expressed in terms of the dilogarithm. So the answer is yes in the Lobachevsky functions. You can find it. And nowadays, because we have so powerful software, you can use Maple. Just typing this, and Maple will tell you the answer. So typing this, Maple can integrate these functions, these integrals now. So it will express in terms of dilogarithm. But if you simplify a little bit, I mean, the expression may be complicated. You need to simplify a little bit, and you will get to this. It's very similar to the formula I mentioned yesterday. It's in fact related to the volumes of hyperbolic tetrahedrons in three-dimensional space, and in some senses, it's not surprising because what Coulomb-Dirichlet guessed this formula is from the Schlafly. It's a three-dimensional one. Okay. Okay. So that's that. Let's now prove the main theorem that I mentioned yesterday, the curve Andreev-Thurston theorem. So as I mentioned, this is a discrete version of Riemann mapping theorem. So let me prove it. I'm going to call this is version 1 because there will be 3 versions. They are all equivalent. But this is the sort of the most complete one and pseudo-symmetric one. I'm going to state the other one in a minute. So for any simplicial triangulation T of the Riemann sphere, we can find a circle packing of the Riemann sphere unique up to Möbius transformation. Such that its nerve, its combinatorics is isomorphic to the first skeleton of the triangulation. Okay, so that's a first version. And so let me prove this. The proof is a combination of Coulomb-de-Radier's method plus Marden. Okay, so combining these two, so here is a proof. Well, so if you look at this picture here, you don't quite see Euclidean triangles come in because we are packing the spheres, and it's probably more natural to use a spherical circle packing. And Marden-Rodin's contribution is just to reduce it to the Euclidean case. So let's take a triangle. So take a triangle in your triangulation, and let's let delta to be the 2 sphere minus the interior of the triangle. So look at the complement of one single triangle, and this will be, and then T produce a triangulation. It's a simplicial triangulation. I'm going to call this T1. Of the triangle delta. Okay, so look at the complement of one single triangle. It's a triangle, and we produce simplicial triangulations. And so let me just draw a picture. Suppose you have this circle packing on the sphere. We have a picture like this. This is a nerve. Okay, so tau is a triangle corresponding to the complement of that, and the rest of the circle packing is inside here. Okay. So that's a picture. Suppose you have a circle packing with a property, and you look at the 3 circles corresponding to the vertices of this tau. We see this picture, and now by the example we proved yesterday, any 3 pairwise tangent circles are Möbius related. Any 2 of them are the same. And so I can use the Möbius transformation and send this guy to 3 circles of the same radii. So this is so suppose let's call the vertices of tau to be v1, v2, v3. And the rest of the circles are here. And now from what I have here, I produce a equilateral triangle. This is a, the tau can be equal to a regular triangle. So by this reduction, you see, to produce a circle packing on the two sphere, it's the same thing as producing a circle packing of this regular triangle. And that's becoming a Euclidean phenomenon. Okay, so this is a normalization process, which is a reduction. So that's the reduction. So this is the second version of, so this is a V2, version 2. By this reduction, this is the version I'm going to prove. And then I'm going to use version 3 to state Thurston's conjecture. Okay. So it says that if T1 is a simplicial, it's a topological triangulation of a regular triangle, delta with V1, V2, V3, whose boundary vertices are V1, V2, V3. So this triangulation is very special. If you look at this, in this case, the nerve of the circle packing is a triangulation of this regular triangle whose boundary vertices are only these three vertices. There are no boundary vertices other than that. And so that's the only picture. So I have a very special triangulation of a triangle of this type. And then the conclusion is that I can produce a circle packing of this triangulation. So then exists a circle packing on this triangle, on this triangulation, such that ROV1, ROV2, ROV3 are specialized. So the three boundary is radii fixed, and that will produce a regular triangulation, and the curvatures are all 0. And the curvature is equal to 0 for all v other than v1, v2, v3. Okay, so that's the equivalence statement, which we are going to prove, and this is now a situation in Euclidean polyhedral geometry. So let's prove this. The proof uses exactly the same argument as I just used for Thurston's case. And so let's play the same game. Let's define a function. So we're going to find this radii by finding the critical point of some functionals. So this is going to be the energy minimizer. So I'm going to define the W hat from V to R by this formula. So W hat. Let me make this a little bit more precise. I'm going to list. So let's list all vertices as V1, V2, V3. These are the three vertices of the original triangle, and the rest of it is V4 and V and so on. Okay. Vn. So that's a list of all vertices. I'm gonna. It's basically the same as what we did before. you look at all triangles VI, VJ, VK in your triangulation. Let's call this T1. And I take the Coulomb-Duvalier subfunctional xi, xj, xk. And now I add some linear correction term to make the curvature correct. So what do I want is for vertices other than the boundary guy, I want the curvature. I mean, this will produce angles, right? So I want the curvature to be 0, and so I will take 2 pi times xi. I is at least 4. And the critical point will give me the cone angle minus 2 pi, which is the negative of the curvature. And so the critical point will be curvature equal to 0. So this correction term is for that. And I also need the correction term for here. So I make I starts from 1 to 3 of the cone angle pi over 3 of xi. So this will take care of this will tell you that the cone angle at the three boundary vertices is 60 degree, and that will force these three radii to be the same. So this is a condition which is equivalent to that. I translate it into here. So I have this function. It's a concave function adding a linear function. This is a concave. And now I claim, suppose you know this function has a critical point and then you are done. So this is the variational principle set up. And I claim you can find a critical point. So claim 1, if you can find a U in RV such that it's a critical point, then we are done. The reason is, as I just explained, right? So indeed, we have partial W partial xi is equal to 2 pi minus the curvature at Vi minus 2 pi for I is at least 4 by exactly the same calculation we just did. And partial W partial xi is equal to 2 pi minus k of Vi. That's a gradient of this functional, and I add a linear term here. Minus pi over 3. So I equals 1, 2, 3, and then we're done. So you have the correct curvatures and correct boundaries, and that's it. So that's easy. And now the second claim is more interesting. The claim number 2 is that this W hat has a maximum point. This is, you see, this statement, in fact, is false if your triangulation is too random. I need to assume simplicial conditions, because you see, you could produce a topological triangulation where it's non-simplicial. You have two vertices joined by 2 distinct edges, and that picture cannot be. So there will be some other triangle stuff inside here. This picture cannot be realized by a circle packing because 2 circles only tangent at 2 points. There's no way you can realize this. So we need to use this condition a little bit to conclude it does have a maximum point. And here, this is really just some of the subtleties comes in. And let me assume this well-known fact. I'm not going to prove it. So here is a lemma by Bean and Starberg. It says the following. So far, what do we have? I have a topological simplicial triangulation of a triangle. So the picture that I draw may be misleading. This is purely topological. This is a topological triangulation. It may not be geometric. And so the picture should draw like this. So the edges may not be straight lines, right? It's purely combinatorics, something like that. And Bean-Starberg theorem lemma says that for this topological triangulation of that, this is isotopic to a geodesic one. So this triangulation is isotopic to a geometric triangulation. T1 of the equilateral triangle. So this is a really interesting phenomenon in 2Ds. All of these topological triangulations, you can really put them tight into geometric one without self-crossing. Okay? And this is no longer true in 3Ds or high dimensional. And this is not too difficult lemma. The proof is time consuming, so I hope everybody can. If you think about it, it's pretty straightforward. Just be careful. Okay, so I'm going to assume this. And this is the part which was not appeared in Thurston's original proof or the other proof. They always run into the same type of issues like this. And they bypass by doing linear programming. This is more complicated. But let me just assume this. I think it should be intuitive enough that everybody should believe it. Okay, so any simplicial triangulations of a triangle can be isotopic to a geometric triangulations. And now take this. So let's let A, I, J, K. It's going to be a positive number. Let it be the angles in T2 at the vertex Vi in the triangle Vi, Vj, Vk. So we can now make this geometric one. I can now produce a actual angle measurement. So this is a topological. I have now T2 here, and now I make all these angle measurement of that. So what do we have for this? For this angles, it satisfies two conditions. First, the sum of the angles in each triangle is equal to pi. That's obvious. And two, if I is at least 4, if the vertex is interior, it's other than the boundary, then the sum of the angle is equal to, the sum of the angles here around is equal to 2 pi. It's a flat structure. So summation jk ai jk is going to be equal to 2 pi. Okay, this is all coming from the geometric triangulation. Now, if the vertex is going to be equal to one of the boundary, then the angle is equal to 60 degrees. So for I equals 1, 2, 3, the summation jk ai jk is equal to pi over 3. Okay, so why do we want to do that? Well, I'm going to rewrite these two quantities, 2 pi here and pi over 3, in terms of these angles. And so I can rewrite it. This function at this moment, it's not clear that you have a maximum point. But if you rewrite it in terms of these positive angles, and you see right away that it has a maximum point. So I can rewrite it. So using these angles Aij, we can write W hat x as a summation over all triangles ijk of this form. W circle packing of xi, xj, xk minus ai, jk, xi, aj, ik, xj, and ak, ij, xk. It's just rewrite it using these two equations. Okay, so the sum of these angles is going to be that. And now what is this? This is exactly, I guess I erased. This is a function g that appears in Coulomb-Divadier's functional. So the GCP. Okay, and these GCPs are proper functions. So now from the corollary, GCP restricted to each of these planes. So U1 plus U2 plus U3 equals 0 is proper. So this function, as u goes to infinity, is going to go to negative infinity. And we conclude, this is almost clear, I hope, that the W, this W function, so W function, when you restrict it, yes, there's always a normalization process because this is circle packing. You can scale it and it produces the same answer. And so you normalize on this plane the sum of all these xi's equal to 0. This function is proper. Okay, so this function goes to minus infinity as x goes to infinity. It's a sum of these functions. Each of that is proper, and it's more or less straightforward. I think I'm not going to go into details. So you can just check it, standard calculus. So this tells you W hat has a maximum point. Okay, so it's a proper function and has a maximum point, and that's a critical point. And we also know from Thurston it's unique. Okay, so that's a proof. I should mention that this notion, and nowadays attract a lot of attention. This was first introduced by Coulomb-Divadier. So these guys are called angle structures. So you just look at these positive numbers satisfy these three equations. Knowing these numbers may not produce a metric for you. There's no geometry you can glue, and these are linear equations and linear inequalities, which is really helpful to detect topology. And so that's the first time that angle structure appeared in literature, and it's now a sort of research topic in three-dimensional geometry and topology. But this is the beginning of the angle structure. So let me just make this remark. The triangulation. Okay, so let me now phrase the third version, version 3 of curve Andreev-Thurston theorem. And this is the one that we are going to use. I mean, in fact, this is the one Thurston used to state his convergence. It's really, they are all equivalent, but this is one which will be a little bit more useful for us. So it says for any simplicial triangulation T of the closed disk d bar. So it's a topological. So you take any simplicial triangulations of a topological closed disk. The point now is that in version 2, we impose a severe condition on the boundary. And now we just impose no conditions. So in version 2, you had only 3 boundaries. And then you can have a circle packing as well. So then there exists a circle packing of the closed disk unique up to Möbius transformation such that, so the picture is now we can circle pack the unit disk. So the condition for the boundary is that every boundary vertex corresponds to a circle tangent to the unit circle, so whose nerve is isomorphic to the first skeleton of that, such that every boundary, every circle corresponding to the boundary vertex is tangent to the unit circle. So circles to boundary are tangent to the unit circle. Okay, so that's a version. Okay, so let me now state what Thurston's conjecture is. Okay, so how do you prove this? The proof is really straightforward. What you do is take this triangulation of the disk, and I produce a new triangulation of the Riemann sphere. So I add one more vertex. This is infinity somewhere here, and I join an edge from this added infinity to every boundary vertex. So by doing that, I produce a simplicial triangulation of the two-sphere. And now you apply Kerr-Andreev theorem to this. I produce a circle packing of the Riemann sphere, whose nerve is this guy. And now you use a Möbius transformation so that the circle corresponding to this V infinity is the unit circle. So this is a circle V infinity. Okay, so that will produce the version 3. Okay, so version 3 is useful because we can now approximate a Jordan domain using this picture. And so here is Thurston's conjecture. I plan to prove it tomorrow. So this afternoon, I will state the discrete conformal geometry versions of that first. So let me state Thurston's conjecture first, and then so let's take omega to be a bounded, simply connected domain in the complex plane. and I take a point in it. So it's something like this. It's my omega, and I take a point in it. By Riemann mapping, so mapping theorem says that you can find a conformal map from your domain to the unit disk. So sending the given point P to the origin, and I normalize that. And so after I normalize it, it's going to be unique. So the normalization is that the derivative at P is positive. Okay, so it sends P to the origin, and the derivative at P is positive. And there's a unique one-to-one onto angle-preserving map between the two. And Thurston's conjecture is trying to approximate this. So this is phi. And here is how he did it. So let's take an integer, take a large integer, and I'm going to produce a circle packing by regular hexagonal circle packing. So let's Pn be a maximum circle packing by circles of the same radius 1 over n. So you fix the n, we're going to pack the whole complex plane by circles of the radius 1 over n. Like this. And so this is Cp inside the omega. And I assume this P is a triangulation of a simply connected disk. Okay, so this is something like this. It's a maximum. This is the maximum circles you can squeeze in, such that Pn is its nerve is a triangulation of a disk. So it will put it into the framework of version 3. So we have a topological triangulations of this. So you will have a picture like this now. It's all regular. And so on. So let's normalize it. So I choose this is my Pn, and let's let Pn be the circle, small Pn, be the circle in Pn whose distance is the most 1 over n to your point P. Okay, so this point, given point P is within some 1 over n distance to some circle. You pick that circle Pn. And now I can use curve Andreev-Thurston theorem version 3. So if you look at the combinatorics of this Pn, you have a simplicial triangulation of a disk. So I can now do a circle packing of that. So there will be a circle packing of the unit disk like this, right? So you can produce a circle packing Qn of the unit disk D, whose combinatorics is the same as Pn. So whose nerve is isomorphic to that of Pn. And I have a choice here, because I can use the Möbius transformation to normalize it. I really need to produce the one which will converge to the correct one. And so let's assume that such that the circle Qn in Qn corresponding to Pn is centered at the origin. Okay, so the one which you pick here, that's your Pn. Now, after Möbius transformation corresponding to the guy which is exactly centered at the origin, and I need, so after you do this normalization, you still have some rotational ambiguities. You can rotate it. And so let me make one more normalization, and that's the one which will converge. And the circle, so Qn prime, corresponding to Pn, small pn plus 2 over n. So this side is a standard. This side is a standard hexagonal triangulation. So you have Pn, there is a 1 next to it. This is a Pn translated by 2 over n. This is the next one to that. So this guy is going to be centered, at the positive x-axis. So this is the one to fix the rotational ambiguities. And now we have this Qn here, and this is a Pn. And we can now produce a piecewise linear map. So let's let Fn be a piecewise linear homeomorphism sending centers of circles in Pn to centers of circles in Qn. So every circle corresponding to one circle, and now I produce so this it's basically it's a point defined. You have a circle here which corresponds to some circle here, just to produce a map, and then on the triangles just extend linearly. And the conjecture is that this is going to converge to the Riemann mapping uniformly on compact subsets. And so Rodin-Sullivan's theorem says it's true. Okay, so it's a beautiful proof, and so I like to tell you. So okay, so this is true. And so nowadays there are softwares which will produce based on this algorithm to find the Riemann mappings. And so if you are interested in seeing these pictures, there are many of them. You Google Ken Stephenson as a book and also software which will produce a lot of circle packings for you. But later on, computer scientists pick this up, and so they produce a much better algorithms, and so much faster algorithm for finding these circle packings. Okay, so that's the circle packing part. I think the next topic will be completely different, and so I may want to stop here now. So this afternoon, I will tell you a different approach to discrete conformality. So this approach here, if you look at this theorem here, the input is topological. So you give me a topological triangulation, and one produce a polyhedral matrix with nice curvature. And if your input is a a polyhedral surface, and you want to do a discrete conformal change, and one need a different setup, and that's what I'm going to cover this afternoon. So I will tell you the relations between the two. So I will stop here. And do you have any questions? Or what's the answer? Pardon?
The answer of this conjecture, the proof that.
So
This proof.
they proved it. So this
current is proven, but
that Rodin-Sullivan proved this conjecture, and I will cover this proof on tomorrow. So I will prove this tomorrow. Okay. Okay. Any other questions? Or? Okay.